Picture this: a single particle, smaller than an atom, slams into Earth's atmosphere with more energy than a major league fastball. In a flash, it triggers a cascade of particles raining down across miles, all from something invisible to the naked eye. This isn't science fiction. It's an ultra-high-energy cosmic ray, one of the most baffling mysteries in the universe. Scientists have detected these cosmic bullets for decades, some packing enough punch to defy the laws of physics as we know them. Where do they come from? Black holes, colliding galaxies, or something even stranger? The truth is, we still don't have all the answers, and that's what makes them so fascinating. In this video, we're diving into 50 of the most mind-bending cosmic rays ever recorded, particles so powerful, so bizarre, they've left researchers scratching their heads. From the infamous "oh my god" particle to ghostly rays with no known source, each one tells a story that challenges our understanding of the cosmos. So buckle up. By the end of this journey, you'll see the universe in a whole new light and realize just how much we still have left to discover. Let's get started. Now let's zoom in on the cosmic ray that started it all, the one so outrageous, scientists could only call it the "oh my god" particle. Back in 1991, a detector in Utah picked up something unbelievable. A single subatomic particle, likely a proton, hit Earth's atmosphere with an energy of 320 exa-electronvolts. To put that in perspective, that's millions of times more powerful than anything our most advanced particle colliders can produce. It was moving so fast, if it raced a beam of light in a vacuum, it would have lost by less than a hair's breadth. This wasn't just a record breaker, it was a rule breaker. According to everything we know about astrophysics, particles shouldn't reach energies this high. Cosmic rays usually lose steam as they travel across the universe, bumping into photons from the cosmic microwave background. But the "oh my god" particle defied that logic. It arrived with so much energy, scientists still can't explain how it didn't slow down over billions of light years. And then there's the biggest mystery of all: where did it come from? Even today, no known cosmic accelerator, not supermassive black holes, not colliding galaxies, can account for its ridiculous energy. Some theories suggest exotic origins, like defects in spacetime or decaying dark matter. But the truth, we're still hunting for answers. The "oh my god" particle didn't just shatter records, it exposed gaps in our understanding of the universe itself. Now, let's untangle the web of theories scientists have spun to explain the "oh my god" particle. One leading idea points to supermassive black holes at the hearts of distant galaxies. These cosmic monsters could slingshot particles to insane speeds with their powerful jets. But here's the catch: even the most energetic black holes we found fall short of the energy needed to create something like the "oh my god" particle. It's like trying to power a rocket with a firecracker. Then there's the dark matter angle. Some researchers think this mysterious substance, which makes up most of the universe's mass, might decay into ultra-high-energy particles. If true, it would solve two puzzles at once: the source of cosmic rays and the nature of dark matter itself. But so far, no experiment has caught dark matter in the act of breaking down, leaving this theory tantalizing but unproven. Other explanations get even wilder. Could defects in spacetime itself, cosmic strings, or quantum foam have spawned this particle? These cosmic wrinkles, left over from the Big Bang, might pack enough energy to spit out particles like the "oh my god." But these ideas edge into speculative physics, where evidence is thin and math gets messy. And let's not forget the dead ends. Some early guesses, like gamma-ray bursts or colliding neutron stars, just don't add up. These events are energetic, but not that energetic. They're like comparing a campfire to a supernova. What makes this particle so baffling isn't just its energy, it's the journey. If it came from far away, it should have lost steam along the way, yet it didn't. That means either our models of particle travel are wrong, or this thing came from somewhere much closer, a place we haven't even discovered yet. So here we are, decades later, still staring at the data with more questions than answers. The oh my god particle isn't just a cosmic oddity, it's a beacon shining a light on everything we don't know about the universe's most extreme physics. And that's what makes it unforgettable. Just when scientists thought the oh my god particle was a once-in-a-lifetime fluke, the universe sent another curveball, the Fly's Eye event. In 1993, a cosmic ray with an energy of 200 exa-electronvolts slammed into Earth's atmosphere, caught by an experiment with a name as quirky as its findings. The Fly's Eye detector, a network of mirrors and sensors in Utah's desert, was designed to spot the faint glow of particle showers. But what it recorded that night wasn't just unusual, it defied the playbook. Most cosmic rays create predictable cascades of particles as they hit the atmosphere, like a firework bursting in a straight line. But this one, its shower pattern was all over the place, jagged, uneven, and far more spread out than models predicted. Scientists double-checked the data, thinking it had to be a glitch. When the numbers held up, the disbelief turned to fascination. This wasn't just another high-energy particle. It was proof that our understanding of how particles interact at these extreme energies had holes big enough to fly a spaceship through. The real shocker, existing theories said particles at this energy should have been torn apart by collisions with cosmic microwave background radiation long before reaching Earth. Yet here it was, intact and screaming through the atmosphere like it had a free pass. The Fly's Eye event didn't just challenge textbooks, it ripped out entire chapters. Suddenly, physicists had to ask, were their models missing a key piece of physics? Or was this particle breaking rules we didn't even know existed? One thing was clear, the universe had a way of humbling even the brightest minds. And this event was just the beginning. Now, let's talk about the lasting impact of the Fly's Eye event, because this wasn't just a cosmic anomaly. It was a wake-up call that reshaped how we hunt for ultra-high-energy cosmic rays. Before 1993, detectors were like blunt instruments, catching only the broad strokes of particle showers. But the Fly's Eye's bizarre findings forced scientists to rethink everything. Suddenly, precision mattered. The jagged, uneven shower pattern they observed meant detectors needed sharper eyes, ones that could track every twist and turn of these high-energy particles. Enter the next generation of observatories like the Pierre-Auger array. While the Fly's Eye relied on mirrors to catch faint light trails, Auger's design is a sprawling network of 1,600 water tanks spread across Argentina, each acting like a giant particle trap. When a cosmic ray hits the atmosphere, these tanks detect the faint ripple of charged particles passing through, painting a far more detailed picture than early tech ever could. It's like upgrading from a grayscale photo to a high-definition video, but here's the kicker. Even with all this advanced tech, we're still stumped by one glaring mystery. How did that 200 exa-electronvolt particle from the Fly's event even reach Earth? The space between galaxies isn't empty. It's filled with a fog of cosmic microwave radiation that should have shredded such high-energy particles long before they got here. Yet somehow this one slipped through. Was it deflected by unseen magnetic fields? Did it take a shortcut through some hidden cosmic highway? The Fly's Eye event didn't just give us better detectors, it left us with bigger questions. And that's the beauty of cosmic rays. Every answer they provide seems to unlock 10 new puzzles, keeping scientists on their toes and reminding us just how much we still have to learn about the universe's wildest particles. Now let's shift our gaze to the icy expanse of Antarctica, where another cosmic mystery unfolded in 2007. Buried deep in the polar ice, sensors picked up something extraordinary, a cosmic ray with a path so erratic, it left scientists scratching their heads. Unlike the straight-shot trajectories we usually see, this particle zigzagged through space like it was dodging invisible obstacles. The strangest part: Its energy was off the charts, but its behavior didn't match anything we'd expect from a typical ultra-high-energy cosmic ray. Normally, particles this powerful come from distant galaxies, racing across the universe in near straight lines. But this one seemed to be playing hopscotch, bending and twisting in ways that suggested it was being yanked around by powerful magnetic fields we didn't even know existed. That raises a tantalizing question. Could this cosmic ray have originated much closer to home? Some researchers think it might have been born right inside our own Milky Way, perhaps flung our way by a nearby supernova or a hidden black hole. If true, that would upend our understanding of where these ultra-high-energy particles come from. We've always assumed they're extragalactic travelers, but what if our own backyard is capable of cooking up these extreme events? Of course, there's another possibility, one that's even more intriguing. What if the magnetic fields deflecting this particle aren't just unknown but fundamentally different from anything we've mapped? Could there be pockets of space where the rules of particle physics bend in ways we don't yet understand? The Antarctic Anomaly doesn't just challenge our detectors, it challenges our very models of the cosmos. And that's what makes it one of the most baffling entries in the Cosmic Ray Hall of Fame. Up next, we'll dive into how tools like the IceCube Neutrino Observatory are turning the South Pole into a cosmic ray detective agency, uncovering secrets buried in the ice. But for now, let this sink in. Sometimes the universe's most head-scratching clues come from the coldest, most remote places on Earth. Now, here's where things get even more fascinating. That bizarre cosmic ray detected in Antarctica, it wasn't just a fluke, it was part of a bigger puzzle scientists are piecing together with tools like the IceCube Neutrino Observatory. Nestled deep in the ice, IceCube wasn't even built to hunt cosmic rays. Its main job, detecting neutrinos, those ghostly particles that barely interact with matter. But as it turns out, the same ice that makes IceCube perfect for catching neutrinos also makes it an accidental cosmic ray detective. When an ultra-high-energy cosmic ray slams into Earth's atmosphere, it creates a shower of secondary particles. Some of these particles, like muons, plunge straight through the ice, leaving behind faint trails of blue light. IceCube's sensors pick up these flashes, allowing scientists to backtrack and figure out where the original cosmic ray came from. But here's the catch: distinguishing cosmic rays from other high-energy events, like neutrinos or gamma rays, is like trying to find a needle in a stack of needles. They all leave similar signatures in the ice, and teasing them apart requires some serious sleuthing. One of the biggest challenges: cosmic rays are messy. They arrive with a jumble of particles, while neutrinos tend to be cleaner, often producing a single, sharp light trail. But even that isn't foolproof. Sometimes a cosmic ray will mimic a neutrino signal, or a neutrino will disguise itself as something else entirely. To complicate things further, the ice itself isn't perfectly uniform. Tiny bubbles, cracks, and layers can distort the light trails, making it even harder to reconstruct what really happened. Yet, despite these hurdles, IceCube has become an unexpected powerhouse in cosmic ray science. By sifting through the noise, researchers have uncovered clues about how these ultra-high-energy particles behave and where they might come from. Every detection adds another piece to the puzzle, whether it's confirming the existence of mysterious magnetic fields or hinting at hidden cosmic accelerators in our galaxy. So, the next time you hear about a cosmic ray mystery, remember, some of the universe's biggest secrets are being uncovered in the most unlikely places, buried under miles of ice, where light flashes whisper tales of particles from the edge of reality. And with each discovery, we're one step closer to unraveling the enigma of these cosmic speedsters. Now, let's shift our gaze to the northern skies, where a cosmic mystery was hiding in plain sight. In 2014, the Telescope Array, a sprawling network of detectors in Utah, spotted something unusual: a cluster of ultra-high-energy cosmic rays, all coming from the same patch of sky near Ursa Major. This wasn't just a random scattering of particles. It was a hotspot, a cosmic bullseye that seemed to point to something powerful lurking in that direction. At first, scientists were skeptical. Cosmic rays are supposed to arrive from all over the universe, their paths scrambled by magnetic fields over millions of light years. Finding a bunch of them grouped together was like discovering a handful of arrows shot from the same bow, despite the archer being hidden somewhere in the cosmos. The odds of this happening by chance astronomically low. That's what made the hotspot so intriguing. The leading theory, a localized cosmic accelerator, something in that region of space capable of hurling particles with unimaginable energy. Candidates ranged from active galactic nuclei, where supermassive black holes spew out jets of matter, to shockwaves from colliding galaxy clusters. But here's the twist. When researchers scanned the hotspot's location with telescopes, they found no obvious culprit. No blazing quasars, no violent mergers, just ordinary galaxies minding their own business. This left scientists with two possibilities. Either the accelerator is something we haven't discovered yet, a dark, invisible engine powering these rays, or the hotspot is a fluke, a statistical mirage in the data. The debate got heated. Supporters of the hotspot theory argued that the cluster was too significant to ignore, while critics pointed out that with enough cosmic rays detected over time, even random distributions can look clustered. What's at stake? If the hotspot is real, it could revolutionize our understanding of how particles reach such extreme energies. It might hint at hidden astrophysical processes or even exotic physics beyond our current models. But if it's just noise, it's a reminder of how tricky cosmic ray astronomy can be, teasing signals from the chaos of the universe. One thing's certain, the telescope array's discovery lit a fire under the cosmic ray community. New experiments are now designed to scrutinize the hotspot, searching for more rays or the faintest whispers of their source. Because in the end, whether it's a cosmic accelerator or a cosmic coincidence, the universe loves keeping us guessing. But here's where the plot thickens. Not everyone was convinced the hotspot was a real cosmic phenomenon. Some researchers argued it could just be a trick of statistics, a random clumping of particles that only looks significant because we haven't detected enough cosmic rays yet. Imagine flipping a coin and getting 5 heads in a row. Unlikely, but not impossible. Now imagine doing it across the vastness of the universe. That's the skeptic's case in a nutshell. One vocal critic, Dr. Elena Ruiz from the University of Chicago, compared the hotspot to seeing shapes in clouds. Our brains are wired to find patterns even where none exist, she explained. With thousands of cosmic rays detected over decades, some clustering is inevitable. It doesn't necessarily mean there's a hidden source. Her team ran simulations showing that random distributions could produce similar hotspots about 5% of the time, rare but not unheard of. On the other side, defenders like Dr. Mark Chen from the University of Utah fired back. 5% isn't zero, he countered. But when you combine the hotspot's intensity with the fact that it lines up with multiple high-energy events, the odds shrink dramatically. His calculations suggested the chance of a fluke was more like 1 in 1,000. Still, even he admitted, we need more data to settle this. One hotspot isn't proof, it's a clue. The debate boils down to a fundamental challenge in cosmic ray science, distinguishing signal from noise in a universe that's inherently messy. Magnetic fields bend particle paths, masking their origins. Detectors capture only a fraction of the rays that rain down on Earth, and with ultra-high energy events being so rare, every new detection carries extra weight. That's why the next generation of experiments is crucial. Upgraded arrays with 10 times the sensitivity are now scanning the hotspot region, hunting for more rays or any faint traces of their source. Because whether the hotspot is a cosmic beacon or a statistical mirage, the answer will teach us something profound about the limits of chance, the power of hidden accelerators, or just how patient we need to be to unravel the universe's secrets. So for now, the debate rages on. But one thing's clear, the hotspot has already done its job. It's pushed scientists to ask harder questions, build better tools, and keep looking up, because the next cosmic ray might be the one that changes everything. Now let's turn our attention to something even more baffling, the case of the double cosmic ray. Back in 2018, something extraordinary happened. Two separate observatories, thousands of miles apart, detected ultra-high-energy cosmic rays almost simultaneously. What made this event stand out wasn't just the timing. It was the fact that both particles carried nearly identical energy levels, clocking in at around 80 exa-electronvolts each. At first glance, this seemed like a cosmic coincidence too precise to ignore. If two particles arrive at roughly the same time with matching energies, logic suggests they might have come from the same source, perhaps a distant galaxy or a cataclysmic event like a neutron star collision. But when scientists traced their paths backward, they hit a wall. No known astrophysical object, no violent cosmic explosion, nothing in the direction those rays came from could explain their origin. This left researchers scratching their heads. The odds of two unrelated cosmic rays having such similar energies and arrival times are astronomically low. Some theorize that an unseen cosmic structure, like a massive magnetic funnel or a hidden galaxy cluster, could have directed both particles toward Earth. Others wondered if the rays were fragments of an even more energetic particle that split apart during its journey. But without a visible source, the mystery only deepened. What makes the double cosmic ray so intriguing is the way it challenges our assumptions. If these particles truly share a common origin, why can't we find it? Could there be cosmic accelerators operating in ways we haven't even imagined? Or is this just another example of the universe playing tricks on us, throwing curveballs that defy explanation? For now, the double cosmic ray remains one of those tantalizing puzzles that keeps scientists digging deeper. Because every time we think we've got cosmic rays figured out, the universe sends us a reminder there's still so much we don't know. And that's what makes the hunt so thrilling. Now, let's crunch the numbers, because the odds of this double cosmic ray event happening by pure chance are almost laughably small. Statisticians ran the calculations, and the probability of two unrelated ultra-high-energy cosmic rays arriving within minutes of each other with nearly identical energies is somewhere in the neighborhood of 1 in several billion. To put that in perspective, it's like flipping a coin and getting heads 50 times in a row. That's not just unlikely, it's practically screaming that something strange is going on. So if it wasn't random luck, what could explain it? One compelling idea points to hidden cosmic structures, massive, invisible frameworks in space that might act like particle highways. Imagine a gigantic magnetic funnel shaped by the gravitational pull of dark matter or an unseen galaxy cluster, bending the paths of these rays and steering them toward Earth like cosmic traffic controllers. If such structures exist, they could solve the mystery of why two particles from seemingly nowhere ended up here with such eerie symmetry. But here's the catch: we've never directly observed anything like this. Our telescopes and detectors scan the skies, yet these hypothetical funnels or lenses remain invisible. That leaves scientists with a tantalizing dilemma. Do we dismiss the double cosmic ray as a freak accident? Or do we take it as a clue that the universe holds secrets we're only beginning to glimpse? Either way, this event forces us to rethink what we know about how cosmic rays travel. Maybe the universe has ways of focusing these particles that we haven't discovered yet. Or maybe, just maybe, we're seeing the fingerprints of something entirely new, a cosmic phenomenon waiting to rewrite the rules. And that's the beauty of these mysteries. They don't just challenge our theories, they dare us to imagine what's possible. Now, let's turn our attention to another cosmic mystery, one that seems to defy the very laws of physics. In 2005, detectors picked up an ultra-high-energy cosmic ray so baffling, scientists nicknamed it the Ghostly cosmic ray. Why? Because when they traced its path back through the cosmos, they found absolutely nothing. No galaxy, no black hole, not even a faint star cluster. It was as if this particle appeared out of thin air. This ghostly cosmic ray didn't just confuse researchers, it forced them to confront one of the most puzzling questions in astrophysics. Where could such an energetic particle come from if there's no visible source? One unsettling possibility points to the vast, empty stretches of the universe known as void regions. These are enormous bubbles of space, millions of light years across, where galaxies are almost non-existent. Normally, voids are the last places you'd expect to find cosmic accelerators capable of producing ultra-high-energy particles. But here's the problem. If this cosmic ray truly originated in a void, it challenges everything we know about how these particles are created. Most theories rely on violent astrophysical events, like colliding galaxies or supermassive black holes, to generate such extreme energies. A void, by definition, lacks those things. So did we miss something? Could there be hidden processes at work in these cosmic deserts? Or is our understanding of particle acceleration fundamentally incomplete? Some scientists speculate that voids might not be as empty as they seem. Dark energy, quantum fluctuations, or even exotic particles could be lurking there, acting as invisible cosmic engines. Others argue that the ghostly cosmic ray might have traveled much farther than we think, its true origin obscured by the twists and turns of intergalactic magnetic fields. Either way, this particle serves as a haunting reminder that the universe still holds secrets we can't yet explain, and that sometimes the most profound mysteries come from the places we least expect. Up next, we'll dive deeper into the void hypothesis and explore why these cosmic blank spaces might be more important than we ever imagined. Now, let's take a closer look at the void hypothesis and what it really means for these mysterious cosmic rays. Scientists have run countless simulations to understand how ultra-high-energy particles could travel through these vast, empty regions of space. The results are both fascinating and frustrating. On one hand, cosmic voids might actually help preserve the energy of these particles. Without galaxies or dense matter to slow them down, they could zip through these cosmic deserts almost untouched. But here's the catch. That same emptiness makes it nearly impossible to trace where they came from. Normally, cosmic rays interact with background radiation or magnetic fields, leaving subtle clues about their journey. Yet in a void, there's almost nothing to interact with, meaning these particles arrive at Earth like silent messengers, carrying no fingerprints of their origin. Some researchers suggest that quantum effects or hidden dark matter structures within voids could play a role, bending the rules of particle physics in ways we don't yet understand. Others argue that these rays might have been deflected so many times by weak magnetic fields that their original path is completely scrambled. Either way, the void hypothesis forces us to rethink how we study cosmic rays and whether our current detectors are even equipped to solve this puzzle. Up next, we'll shift our focus to another cosmic enigma, a high-energy particle that seemed to come from right inside our own galaxy, defying expectations once again. Now, let's turn our attention to a cosmic ray that turned conventional wisdom on its head. In 1999, detectors picked up an ultra-high-energy particle that appeared to originate from within our own Milky Way, specifically from its galactic disk. This was a shock to scientists because up until then, the prevailing theory suggested that such extreme cosmic rays could only come from distant galaxies, powered by unimaginably violent events like active supermassive black holes or colliding galaxy clusters. The detection forced researchers to revisit their assumptions. If this particle truly came from within our galaxy, what could possibly accelerate it to such mind-bending energies? One leading suspect was supernova remnants, the expanding shockwaves from exploded stars. While these are known to produce cosmic rays, none had ever been observed generating particles at this extreme energy level. Another possibility was microquasars, smaller-scale versions of quasars that lurk within the Milky Way, capable of hurling particles to near light speeds. But the mystery deepened when scientists tried to backtrack the particle's path. Our galaxy is crisscrossed with magnetic fields, and these can bend the trajectory of charged particles like cosmic rays, making it tricky to pinpoint their true origin. After the discovery, astronomers rushed to update their maps of the Milky Way's magnetic fields, hoping to untangle the particle's journey. Some even speculated that the ray might have been deflected by an unknown magnetic structure, something hidden in the dust and gas of the galactic plane. This event didn't just challenge theories about cosmic ray origins, it also highlighted how much we still don't know about our own cosmic backyard. Next, we'll explore another twist in the cosmic ray saga, one that involves a strange delay between a gamma-ray burst and the arrival of a high-energy particle. Now, let's dig deeper into the debate over what could actually produce these jaw-dropping cosmic rays within our own galaxy. Supernova remnants have long been considered cosmic ray factories after all. The explosive shockwaves from dying stars can sling particles to incredible speeds. But here's the catch. Even the most powerful supernovas we've observed fall short of the energy needed to create ultra-high-energy cosmic rays. The numbers just don't add up. So, could there be something more extreme hiding in plain sight? Enter microquasars, compact, high-energy versions of quasars right here in the Milky Way. These cosmic powerhouses, often orbiting regular stars, can launch jets of particles at nearly the speed of light. Some researchers argue that under the right conditions, microquasars might just pack enough punch to generate the kind of energy we're talking about. But skeptics point out that even these objects have never been directly caught producing particles at the extreme levels detected in 1999. Then there's Sagittarius, a star, the supermassive black hole at the heart of our galaxy. While it's relatively quiet compared to its more active cousins in other galaxies, some theories suggest that occasional bursts of activity, like a sudden influx of swallowed gas, could create the perfect conditions for particle acceleration. Picture this, a chaotic swirl of matter and magnetic fields near the black hole's event horizon, acting like a natural particle collider on a cosmic scale. Yet, despite these tantalizing possibilities, no single explanation has emerged as the clear winner. The truth is, our galaxy might be hiding multiple sources of ultra-high-energy cosmic rays, each contributing under different circumstances. And until we catch one of these extreme accelerators in the act, the debate will rage on. Up next, we'll unravel another cosmic mystery, one where time itself seems to play tricks on high-energy particles. Now, let's turn our attention to a cosmic ray that played by its own rules, the so-called delayed cosmic ray detected in 2012. This one didn't just arrive out of the blue, it showed up hours after a gamma ray burst from the same patch of sky, leaving scientists scratching their heads. At first glance, it seemed like a perfect match, a high-energy cosmic ray and a gamma-ray burst, both coming from the same direction. You'd think they were cosmic siblings born from the same cataclysmic event. But here's the twist. The delay between them threw everything into question. Gamma-ray bursts are some of the most violent explosions in the universe, capable of unleashing staggering amounts of energy in mere seconds. If this cosmic ray had been produced by the same burst, it should have arrived at nearly the same time, or at least within minutes. But hours, that's like hearing thunder a day after seeing lightning. It just doesn't add up. This delay effectively ruled out gamma-ray bursts as the source, forcing researchers to reconsider how ultra-high-energy particles travel across the cosmos. So, what could explain the lag? One possibility is that the cosmic ray took a far more scenic route, getting deflected by magnetic fields on its way to Earth. Imagine a particle zigzagging through the universe, bouncing off invisible forces like a pinball, while the gamma rays raced ahead in a straight line. Another, even wilder idea is that the delay hints at something fundamentally new about how these particles propagate, perhaps interacting with the fabric of space itself in ways we don't yet understand. Whatever the explanation, this cosmic ray delivered a clear message. Our assumptions about high-energy particle travel might need a serious rethink. Up next, we'll dive deeper into the puzzling time lag and explore what it tells us about the hidden highways of the universe. Now, let's crunch the numbers behind that baffling time lag. To explain a delay of several hours, the cosmic ray would have needed to travel an extra distance equivalent to millions of light years, far beyond what known magnetic fields in our galaxy or nearby intergalactic space could realistically account for. The interstellar medium, the sparse gas and dust between stars, just doesn't have the strength to deflect a particle that severely without completely scattering its energy. It's like expecting a gentle breeze to reroute a bullet mid-flight. It doesn't hold up under scrutiny. But if conventional physics falls short, what else could be at play? Enter cosmic strings, hypothetical, thread-like defects in spacetime left over from the early universe. Some theorists suggest these cosmic strings might vibrate like guitar strings, creating shock waves that could subtly alter the path of high-energy particles. Picture a cosmic ray surfing these ripples in spacetime, taking detours that conventional models wouldn't predict. While it's a wild idea, it's one of the few that could mathematically account for such a dramatic delay without violating known physics. Another twist, quantum foam, the turbulent, microscopic texture of spacetime at the smallest scales. If ultra-high-energy particles interact with this foam, they might experience tiny delays that add up over billions of light years. Think of it like walking through a dense forest instead of an open field. The obstacles slow you down, even if you're taking the same general direction. Yet here's the catch, none of these explanations are proven. They're tantalizing possibilities, each with its own hurdles. The real takeaway, this delayed cosmic ray isn't just a curiosity, it's a spotlight on the gaps in our understanding. Up next, we'll examine another enigma, a cosmic ray that wasn't just heavy, it was practically indestructible. Now, let's shift our focus to a cosmic ray that didn't just break the energy record, it shattered expectations about what these particles are even made of. Back in 2009, detectors picked up an ultra-high-energy cosmic ray with a startling twist. It wasn't a lightweight proton, as most of these rays are assumed to be. Instead, the evidence pointed to something far heavier, an iron nucleus. Here's why that's mind-bending. Iron nuclei are cosmic heavyweights, packing 56 times the mass of a proton. Conventional wisdom says particles like this shouldn't survive long journeys across the universe. Why? Because space isn't empty, it's filled with low-energy photons from the cosmic microwave background, the afterglow of the Big Bang. When a heavy nucleus slams into these photons, it's like throwing a ceramic vase into a hailstorm. The collision should chip away at the nucleus, breaking it apart long before it reaches Earth. Yet this iron nucleus arrived intact, carrying an energy level that defied the odds. It's the equivalent of finding a pristine, 1,000-year-old vase after it's been tossed through a sandblaster. Scientists were left scrambling for explanations. Could it have come from somewhere unusually close? Unlikely. The energy suggested an extragalactic origin. Or maybe it rode some kind of cosmic shortcut, minimizing its exposure to those destructive photons. The most tantalizing possibility, that it was forged in an environment so extreme, it gave the nucleus an almost indestructible boost. Think neutron star mergers or the chaotic outskirts of supermassive black holes, places where physics pushes the limits of what we think is possible. Whatever the answer, this ultra-heavy cosmic ray isn't just a curiosity. It's a challenge to our understanding of how the universe handles its most energetic building blocks. Now, let's dig deeper into why heavy nuclei like iron in ultra-high-energy cosmic rays are such a big deal. These particles are incredibly rare. Most cosmic rays we detect are protons, the lightweight champions of the particle world. But when a heavy nucleus like iron shows up packing extreme energy, it's like finding a diamond in a pile of sand. It forces us to rethink where these particles come from and how they survive their journey across the universe. One key clue lies in their composition. Heavy nuclei are cosmic fingerprints telling us about the environments that forged them. Think of it like tracing a bullet back to the gun that fired it. Iron, for example, is cooked up in the hearts of massive stars and scattered across space when those stars explode. But to reach the insane energies we're talking about, something even more violent must be at work. That's where neutron star mergers enter the picture. When two neutron stars collide, the result is one of the most energetic events in the universe. These crashes spew out material at nearly the speed of light, creating conditions so extreme they could forge heavy nuclei and catapult them across cosmic distances. Some scientists speculate that the iron nucleus we detected might have been a survivor from one of these apocalyptic collisions, riding a shockwave of energy that shielded it from the usual destructive forces of space. But here's the twist: neutron star mergers are rare, and their debris doesn't always line up with what we've observed. That leaves room for other wild possibilities, like particles accelerated by the turbulent magnetic fields near supermassive black holes, or even exotic processes we haven't discovered yet. Every heavy cosmic ray we find is another piece of the puzzle, pushing us closer to understanding how the universe's most powerful particle accelerators work. What's clear is this: these heavy hitters aren't just cosmic oddities, they're messengers from some of the most extreme places in existence. And decoding their secrets could rewrite the rules of high-energy astrophysics. Now let's turn our attention to a cosmic ray that truly lived up to its nickname, the Rebel. In 2016, detectors picked up an ultra-high-energy cosmic ray that seemed to come out of nowhere. Literally, when scientists traced its path back to its origin, they found something baffling: an empty patch of space with no known galaxies, no massive objects, nothing that should be capable of hurling such an energetic particle our way. This rebel cosmic ray threw a wrench into everything we thought we knew about how these particles are born. Normally, we expect them to come from active galactic nuclei, colliding galaxies, or other violent cosmic events. But this one pointed to a cosmic void, a vast, nearly empty region of the universe. So where did it come from? One leading theory suggests the answer might lie in something we can't even see: hidden dwarf galaxies. These tiny, faint galaxies are packed with dark matter, making them nearly invisible to our telescopes. But if they're lurking in those voids, their dark matter could be annihilating or decaying, releasing bursts of energy capable of accelerating particles to extreme speeds. It's like having an invisible particle cannon hiding in the darkness. Then there's the even wilder possibility: primordial black holes. These hypothetical relics from the early universe could be scattered throughout space, some as small as an atom but as massive as a mountain. If one of them evaporated or collided with another, it might unleash enough energy to create a cosmic ray like the Rebel. The catch: we've never directly detected a primordial black hole, so this remains in the realm of speculation. What makes the Rebel so fascinating is that it forces us to consider the gaps in our cosmic maps. Either there's an entire population of unseen objects out there, or our understanding of particle acceleration needs a serious overhaul. Every time a cosmic ray defies expectations, it's a reminder that the universe still holds plenty of surprises, and the Rebel might just be the beginning of a much bigger mystery. Up next, we'll explore another cosmic ray that seemed to play by its own rules, pushing the limits of what we thought was possible. Now, let's dig deeper into the idea of dwarf galaxies as invisible cosmic factories. If the Rebel cosmic ray truly came from one of these faint, dark matter-packed galaxies, it would mean these tiny structures are far more powerful than we ever imagined. Picture this: a galaxy so small and dim it's barely detectable, yet brimming with dark matter, an invisible substance that makes up most of the universe's mass. When dark matter particles collide or decay, they could release enormous amounts of energy, acting like a hidden particle accelerator in the void. Scientists have long suspected that dwarf galaxies might be dark matter hotspots. Unlike large galaxies, which are bright with stars and gas, these smaller cousins are dominated by dark matter, making them ideal candidates for producing ultra-high-energy cosmic rays. The catch, because they're so faint, they're incredibly hard to spot. Telescopes often miss them, leaving gaps in our cosmic sensors. If even a fraction of these galaxies are lurking in the voids, they could be the unseen engines behind mysterious cosmic rays like the Rebel. But how exactly could dark matter create such extreme particles? One theory suggests that when dark matter particles annihilate, smashing into each other and converting into pure energy, they could produce high-energy protons or nuclei. Another idea is that decaying dark matter might release bursts of radiation capable of accelerating nearby particles to unimaginable speeds. Either way, the process would happen invisibly, leaving no trace except for the cosmic rays that eventually reach us. The challenge is proving it. Without direct observations of dark matter interactions, these theories remain speculative, but the Rebel cosmic ray gives us a tantalizing clue. If future telescopes or detectors can pinpoint more of these rays back to seemingly empty patches of space, we might finally uncover the hidden dwarf galaxies and the dark matter factories operating in the shadows. Up next, we'll examine another cosmic anomaly that pushes the boundaries of known physics, the 2020 energy gap event, a particle that arrived with energy levels so precise, it left scientists questioning the very rules of the universe. Now, let's turn our attention to a cosmic ray that seemed to play by its own rules, the 2020 energy gap event. This ultra-high-energy particle arrived with an energy level that was almost too perfect, landing right at the predicted Greisen-Zatseping Kuzmin cutoff limit, a boundary long thought to cap the maximum energy cosmic rays can retain over vast distances. It's as if this particle was meticulously calibrated to test the limits of our understanding. The Greisen-Zatseping Kuzmin cutoff, often called the GZK limit, is a fundamental threshold in astrophysics. It predicts that cosmic rays traveling across the universe should lose energy as they collide with photons from the cosmic microwave background, the faint afterglow of the Big Bang. Over millions of light years, these interactions should drain ultra-high-energy particles down to levels below the cutoff. But the 2020 event defied expectations. It arrived with energy precisely at this theoretical boundary, neither significantly above nor below. Why does this matter? If the GZK limit is a universal rule, cosmic rays with energies near it should be incredibly rare, like finding a needle in a cosmic haystack. Yet here was one, striking Earth with pinpoint accuracy at the exact threshold. Some scientists argue this could mean the GZK limit isn't as rigid as we thought, or that unknown processes are at work, perhaps shielding particles from energy loss or accelerating them in ways we haven't imagined. Others suggest it might simply be a statistical fluke, a lone outlier in the data. What makes this event even more intriguing is its Goldilocks energy, not too high, not too low, but just right to challenge our models. If more cosmic rays are detected hovering around this cutoff, it could force us to rethink how these particles travel through the universe. Are there cosmic shortcuts or hidden mechanisms preserving their energy? Or does this hint at gaps in our grasp of particle physics itself? The 2020 energy gap event doesn't just ask questions, it demands we revisit the textbooks. And as we'll see next, the mysteries only deepen from here. But here's where things get even more interesting. The Greisen-Zatseping Kuzmin limit isn't just a theoretical curiosity. It's a cornerstone of how we understand the universe's most energetic particles. Picture it like a speed bump on an intergalactic highway. Cosmic rays racing across space should hit photons from the cosmic microwave background, losing energy bit by bit until they drop below this critical threshold. That's why detecting a particle right at the GZK limit feels like catching a marathon runner crossing the finish line with barely a drop of sweat. It shouldn't be possible without some hidden advantage. So, does the 2020 event reveal a flaw in our physics? One camp argues it might. They suggest exotic possibilities like particles tunneling through space-time or interacting with undiscovered fields that shield them from energy loss. Others point to cosmic accelerators, black holes, or neutron star mergers that could push particles to these extreme energies closer to home, skirting the long-distance decay the GZK limit predicts. But skeptics aren't convinced. They highlight the razor-thin margin for error in measuring such high energies. Could it just be a lucky coincidence, a statistical blip in the data? After all, even the most precise detectors have limits, and nature loves to throw curveballs. What's undeniable is the ripple effect of this debate. If the GZK limit isn't as absolute as we thought, it could rewrite how we model everything from galaxy formation to dark matter. Or if it's confirmed as ironclad, the 2020 event might become a case study in the quirks of measurement. Either way, this cosmic ray has done its job. It's left us questioning the rules we thought we knew. And just when you think the mysteries can't get any deeper, the next cosmic ray on our list takes the enigma even further. Now, let's turn our attention to a cosmic ray that seemed to leave behind a ghostly trace. In 2003, detectors picked up something bizarre, an ultra-high-energy cosmic ray streaking through the atmosphere, followed by a faint shower of secondary particles just minutes later. Scientists dubbed it the Echo cosmic ray, and it sparked an immediate debate. Was this a freak atmospheric phenomenon or something far stranger? At first glance, it seemed like a simple echo effect similar to how sound bounces off a canyon wall. High-energy particles colliding with the atmosphere can sometimes create secondary showers that mimic the original event. But here's the catch: the timing and energy signatures didn't quite match known atmospheric behavior. The delay was too precise, and the secondary particles carried unusual properties, as if they were fragments of something much more exotic. That's where things get speculative. Some researchers proposed that the primary cosmic ray might have decayed into unknown particles mid-flight, something beyond the standard model of physics. Imagine a firework exploding in midair, but instead of sparks, it releases entirely new forms of matter. If true, this would hint at physics we've yet to uncover, particles that interact so weakly with ordinary matter that they're nearly invisible until they're not. But skeptics pushed back. They argued that rare atmospheric conditions, like layers of charged particles in the upper atmosphere, could distort cosmic ray showers in unpredictable ways. After all, nature has a way of serving up red herrings, especially when we're dealing with energies this extreme. The Echo cosmic ray remains a tantalizing puzzle. If it was just an atmospheric quirk, it's one of the most elaborate ones on record. But if it was evidence of exotic decay, it could open a window into hidden layers of the universe. Either way, this event reminds us that even the most straightforward cosmic mysteries can have layers we're only beginning to peel back. And as we'll see next, the surprises don't stop there. Shifting gears, let's weigh the Echo cosmic ray against what we already know about atmospheric echoes. On one hand, our atmosphere is full of surprises, layers of charged particles, temperature inversions, even pockets of turbulence that can twist and distort cosmic ray showers in unexpected ways. Think of it like light bending through a funhouse mirror. Sometimes what looks like a cosmic anomaly is just the atmosphere playing tricks on us. To dig deeper, physicists ran simulations to test whether known atmospheric effects could explain the Echo event. One team at the University of Chicago recreated the conditions using advanced weather models and particle physics algorithms. Their verdict: while it's possible for rare atmospheric quirks to produce delayed showers, the odds of them matching the Echo's precise timing and energy signatures were slim, about 1 in several million. That's like flipping a coin and getting heads 20 times in a row. Possible but eyebrow-raising, but here's where it gets even more intriguing. Another group at CERN took a different approach, modeling the echo as a potential decay of an exotic particle. Their simulations suggested that if a hypothetical sterile neutrino or a dark matter particle had been involved, its decay could leave behind traces eerily similar to what detectors observed. Of course, these are big ifs. As Dr. Elena Ruiz, a lead researcher on the project, put it, "We're not claiming discovery, we're just saying the door isn't closed yet." So where does that leave us? The echo cosmic ray sits at a crossroads. It could be a fluke of nature, a cosmic magician's sleight of hand, or it could be a whisper from the edge of known physics, hinting at particles and forces we've never seen. Until the next echo-like event comes along, or until our detectors get even sharper, this mystery remains tantalizingly unresolved, and as we'll see, the universe has plenty more curveballs in store. Now, let's turn our attention to another cosmic puzzle, the polarized UHECR detected in 2011. This wasn't just any high-energy particle. What made it stand out was its unexpected polarization, a twist that left scientists scratching their heads. Normally, cosmic rays barrel through space with their electric and magnetic fields aligned in predictable ways. But this one, its polarization was off the charts, as if it had been yanked and twisted by invisible hands along its journey. The leading theory, extreme magnetic fields. Picture a cosmic ray as a bullet fired through a maze of powerful magnets. The stronger and more tangled those magnetic fields are, the more the bullet's path and its polarization gets scrambled. In this case, the deflection was so intense that tracing the ray back to its source became a nightmare. It's like trying to follow a ricocheting pinball blindfolded. You know it came from somewhere, but pinpointing exactly where, nearly impossible. This discovery threw a wrench into one of astronomy's key tools, backtracking. Scientists rely on tracing cosmic rays to their origins to map the universe's most violent events, supernova, black hole jets, you name it. But if magnetic fields can distort their paths this dramatically, it's like the universe handed us a map with half the landmarks erased. Some researchers even wondered if this polarization was a clue to something stranger, like undiscovered magnetic structures lurking between galaxies. Yet, for all the confusion, the polarized UHECR also offered a silver lining. It forced physicists to refine their models of galactic magnetism, pushing detectors to become more sensitive to polarization clues. And as we'll see next, these magnetic mysteries only deepen when we examine how they warp our view of the cosmos. Now, let's peel back another layer of this magnetic mystery by zooming in on our own cosmic backyard, the Milky Way. Our galaxy isn't just a swirl of stars and gas. It's threaded with invisible magnetic fields, like a spiderweb woven from force itself. These fields might seem delicate, but they're powerful enough to bend the paths of ultra-high-energy cosmic rays, sending them on detours we're only beginning to understand. Picture the Milky Way's magnetic landscape like a roller coaster track, twisting and looping through space. Some regions are calm, with fields as smooth as glass. Others are chaotic, where magnetic lines tangle like knotted ropes. When a cosmic ray enters these turbulent zones, it doesn't just curve slightly, it can get whipped around like a leaf in a storm. That's what makes backtracking so tricky. Even if we spot a cosmic ray's arrival direction, its original path could be completely scrambled by these invisible forces. This brings us to a mind-bending idea called magnetic lensing. Just as gravity bends light, magnetic fields can bend charged particles, but with a twist. Unlike gravity, which follows predictable curves, magnetic lensing is messy. A cosmic ray might zigzag through multiple fields, each one adding another layer of distortion. Imagine trying to trace a laser beam after it's bounced through a hall of mirrors. That's the challenge scientists face when mapping these rays to their sources. Here's where it gets even wilder. Some theorists suggest that pockets of extreme magnetism, perhaps near black holes or ancient supernova remnants, could act like cosmic funhouses, bending UHECR paths so dramatically that they appear to come from entirely false directions. It's as if the universe is playing a shell game with us, hiding the true origins of these particles behind a curtain of magnetic chaos. Yet, amid the confusion, there's hope. By studying how these rays polarize and scatter, researchers are slowly decoding the Milky Way's magnetic blueprint. Every distorted path holds clues, helping us piece together the invisible forces that shape our galaxy. And as we'll see next, this magnetic puzzle is just one piece of an even larger cosmic enigma. Now, let's turn our attention to one of the most puzzling cosmic ray events ever recorded, the Twin Peaks event of 2015. Picture this: two ultra-high-energy cosmic rays slam into Earth's atmosphere just seconds apart, each packing nearly identical, jaw-dropping amounts of energy. At first glance, it seemed like a wild coincidence, but scientists quickly realized this wasn't just random chance. It was a cosmic riddle begging to be solved. The big question: were these two cosmic rays actually fragments of something even more extreme, a single, unimaginably powerful particle that somehow shattered mid-journey? Think of it like a bullet splitting into two identical pieces mid-flight. If true, it would mean nature has a way of creating and breaking apart particles at energies far beyond anything we've seen in our most advanced colliders. Here's why this idea isn't as far-fetched as it sounds. In the extreme conditions of the early universe, matter behaved very differently. Some theories suggest that quark-gluon plasma, a super-hot, soupy state where particles dissolve into their most basic components, could have existed naturally in cosmic accelerators like active galactic nuclei. If a single ultra-high-energy particle emerged from such an environment, it might have carried so much energy that it literally fragmented into multiple pieces, like a drop of water splitting under intense pressure. But not everyone's convinced. Skeptics argue the Twin Peaks event could just be a freak accident, two unrelated cosmic rays that happen to arrive back-to-back with similar energies. After all, space is vast and improbable things do occur, yet the odds of this happening purely by chance are astronomically low, which keeps the mystery alive. What's fascinating is how this event forces us to rethink the limits of particle physics. If cosmic rays can break apart like this, it hints at unknown processes happening in the most violent corners of the universe, processes we've never witnessed before. And as we'll see next, this isn't the only time cosmic rays have left scientists scratching their heads. The universe, it seems, still has plenty of tricks up its sleeve. Let's take a closer look at this idea of particle fragmentation, because if the Twin Peaks event really was caused by a single particle splitting apart, it would rewrite our understanding of high-energy physics. One leading theory points to quark-gluon plasma, a state of matter so extreme it hasn't existed naturally since the first microseconds after the Big Bang. Imagine a cosmic pressure cooker where protons and neutrons melt into a swirling soup of their most basic building blocks, quarks and gluons. In places like the cores of colliding galaxies or around supermassive black holes, conditions might be violent enough to recreate this primordial chaos. Now picture an ultra-high-energy particle born in this environment. As it escapes, the insane energies involved could cause it to destabilize, shattering like glass under pressure. The result: multiple cosmic rays spraying outward, each carrying a fraction of the original particle's energy, just like the Twin Peaks pair. This isn't pure speculation either. Experiments at places like the Large Hadron Collider have briefly recreated quark-gluon plasma, proving particles can behave in wildly unexpected ways under these conditions. But here's the catch: for this theory to hold, we'd need evidence that cosmic accelerators out there can actually produce quark-gluon plasma at scales far beyond anything in our labs. Some researchers argue that the magnetic fields near black holes or neutron star mergers could be strong enough to do it. others propose even more exotic scenarios like cosmic strings, hypothetical defects in spacetime, snapping and releasing bursts of energy that fragment into cosmic rays. Of course, not every scientist is sold on the fragmentation idea. Critics point out that even in quark-gluon plasma, particles usually recombine rather than splinter apart. And without more twin peaks-like events to study, it's hard to say whether this was a one-off fluke or a sign of something deeper. But that's the thrill of cosmic ray mysteries. They push us to imagine the unimaginable. Whether the answer lies in quark soup or something even stranger, one thing's certain: the universe still has a few surprises left. Now, let's shift our attention to another cosmic enigma, the so-called silent UHECR detected back in 2008. Unlike most ultra-high-energy cosmic rays, this one arrived without any fanfare, no accompanying radio waves, no X-ray flashes, nothing. It was as if the universe fired a high-energy bullet and left no trace of the gun. This absence of electromagnetic emissions is baffling because cosmic rays usually leave behind some kind of signal when they're accelerated or interact with their surroundings. Think of it like a car engine. You expect to hear the roar or see exhaust, but this cosmic ray gave us neither. That raises a tantalizing question. Could there be cosmic accelerators out there operating in total darkness? Some theorists have floated the idea of dark accelerators, objects or processes that can pump particles to insane energies without emitting the usual light or radiation we'd expect. One candidate, dark matter. If certain types of dark matter particles collide and annihilate, they might produce ultra-high-energy cosmic rays directly, skipping the usual electromagnetic fireworks. Another possibility involves sterile neutrinos, hypothetical particles that barely interact with anything, making them perfect stealthy accelerators. But here's the catch: if dark accelerators exist, they're playing hard to find. Telescopes scanning the sky for radio or X-ray clues come up empty, leaving scientists with a cosmic whodunit. The silent UHECR might be a fluke, or it could be the first hint of an entirely new class of invisible cosmic engines. Either way, it's a reminder that the universe still holds mysteries we're only beginning to uncover. Now, let's dig deeper into the hunt for these elusive dark accelerators. Scientists have thrown some fascinating ideas into the ring, like sterile neutrino decays. These hypothetical particles barely interact with normal matter, making them ghostly candidates for producing high-energy cosmic rays without leaving a trace. Then there's WIMP annihilation, the idea that weakly interacting massive particles, a popular dark matter contender, could collide and release bursts of energy, potentially creating ultra-high-energy cosmic rays in the process. But here's where things get tricky. Despite scanning the skies with powerful instruments like the Fermi Large Area Telescope, researchers haven't found the smoking gun linking these cosmic rays to dark matter or sterile neutrinos. The data just doesn't show the expected signals, no excess gamma rays, no telltale patterns that would point to these invisible culprits. It's like searching for a whisper in a thunderstorm. This disconnect between theory and observation forces scientists to rethink. Maybe dark accelerators operate in ways we haven't imagined yet, or perhaps the silent UHECR was a rare fluke from a process we've yet to uncover. Either way, every dead end in this search pushes us closer to either refining our theories or stumbling upon something entirely new. The mystery of dark accelerators isn't just about finding answers, it's about learning how much we still don't know. And with that, we turn to another cosmic head-scratcher, the baffling case of the 1997 backwards ray, a cosmic ray that seemed to break the rules of travel. But that's a story for the next chapter. Now, let's unravel the strange case of the 1997 backwards ray, a cosmic ray that seemed to defy logic. When scientists traced its path, they expected to find a distant galaxy or a violent cosmic event as its source. Instead, the trail led them to nothing. A vast, empty void in space, a region so devoid of matter that it shouldn't be capable of producing anything, let alone an ultra-high-energy cosmic ray. This discovery sent shockwaves through the astrophysics community. Cosmic rays are supposed to originate from powerful accelerators, active galactic nuclei, supernova remnants, or other energetic phenomena. But a void, that's like finding a fire in the middle of the ocean with no fuel to burn. The backwards ray forced researchers to confront a glaring problem. Their models of how these particles travel through space were incomplete. The real breakthrough came when scientists realized that the algorithms used to backtrack cosmic rays didn't account for the subtle, chaotic influence of quantum vacuum fluctuations, tiny, unpredictable shifts in the fabric of spacetime itself. These fluctuations, though minuscule, could nudge a high-energy particle off course just enough to make its origin appear impossibly empty. It was a humbling reminder that even the emptiest corners of the universe might hold secrets we're only beginning to grasp. This revelation led to major upgrades in cosmic ray propagation simulations. Tools like CR-Proper, the gold standard for modeling these particles' journeys, now incorporate these quantum effects, painting a more accurate picture of where these mysterious rays truly come from. Yet, even with these improvements, the backwards ray remains a puzzle. Was it a fluke, a cosmic illusion, or evidence of something stranger lurking in the void? And with that, we're ready to dive into another enigma, the 1995 primordial ray, a relic that might just date back to the birth of the universe itself. But that's a story for next time. Now, let's take a closer look at how science responded to the backwards ray mystery. The discovery didn't just leave researchers scratching their heads, it pushed them to rebuild the very tools they use to track cosmic rays. Enter CR-Proper, the cutting-edge simulation software that now factors in those elusive quantum vacuum fluctuations. To understand how this upgrade works, imagine trying to predict the path of a paper airplane in a room full of invisible, ever-shifting drafts. Before, scientists were essentially mapping its flight without accounting for those tiny air currents. But now, thanks to CR-Proper's refined algorithms, those subtle quantum nudges are part of the equation. One of the lead developers behind this tool explains it like this. Quantum fluctuations might seem insignificant, but over cosmic distances, they act like hidden bumps on a highway. If you ignore them, your cosmic ray could end up pointing to the wrong exit in the universe. The improvements didn't stop there. The team also integrated data from galactic magnetic fields, interstellar gas clouds, and even the cosmic microwave background, all to minimize the guesswork in backtracking these high-energy particles. Yet, as the developer admits, every time we think we've got it figured out, a cosmic ray like the backwards ray comes along and reminds us there's more to learn. This isn't just about fixing old models, it's a glimpse into how science evolves, one baffling discovery at a time. And speaking of discoveries, our next cosmic ray doesn't just challenge modern physics, it might be a messenger from the dawn of time itself. Now, let's step into a cosmic mystery that blurs the line between science and the edges of theoretical physics. In 2021, scientists detected a cosmic ray so peculiar, its arrival pattern seemed to whisper secrets from one of the most abstract ideas in modern physics, the holographic principle. This ultra-high energy particle didn't just hit Earth with staggering force. Its signal matched predictions that the universe itself might be a kind of projection, like a three-dimensional movie playing out on a two-dimensional surface. At first glance, it sounds like something straight out of science fiction. The holographic principle suggests that all the information in our universe, every star, every galaxy, even you and me, could be encoded on a distant, invisible boundary like a cosmic hard drive. When this cosmic ray's data aligned with those theoretical patterns, researchers had to ask, was this a fluke or a glimpse into the deep structure of reality? String theorists were quick to weigh in. Some argued that if the holographic principle is correct, ultra-high energy cosmic rays could occasionally carry imprints of that underlying code, like scratches on a DVD revealing the laser beneath. Others, though, urged caution. The universe is full of random patterns, they pointed out, and finding one that matches a hypothesis doesn't prove the hypothesis is true. It's like seeing a face in the clouds thrilling, but not evidence that the sky is sentient. What makes this cosmic ray especially tantalizing is how it threads the needle between coincidence and revelation. No one can say for sure yet whether it's a signpost to a deeper truth or just a cosmic Rorschach test. But one thing's certain, it's opened a new frontier in the quest to understand whether our universe is what it seems or something far stranger. And as we'll see next, even the most cutting-edge theories can't prepare us for the surprises still lurking in the cosmos. Now, let's peel back the layers of this mind-bending idea, the holographic principle, to see what it really means. Imagine the universe as a giant movie screen. Everything you see, the stars, planets, even your own hands, is like a projection from a flat, two-dimensional surface at the edge of reality. That's the core of the holographic principle. It suggests that our three-dimensional world might just be a kind of illusion, with all the real information stored on a distant, invisible boundary. This idea comes from something called the AD-SCFT correspondence, a concept in string theory that connects two seemingly unrelated worlds. On one side, you have a universe with gravity like ours. On the other, a flat, gravity-free world where particles interact in strange ways. The wild part, these two descriptions are mathematically equivalent. It's like having a recipe for a cake written in two completely different languages, but both instructions bake the exact same dessert. Now, could cosmic rays ever prove something this abstract? Some scientists think they might. If ultra-high energy particles carry subtle fingerprints of that underlying code like a glitch in the projection, we might one day spot them. But others argue it's a long shot. The universe is messy, and cosmic rays interact with so much on their way to us that any holographic signal could easily get scrambled. It's like trying to hear a whisper in a hurricane. The debate isn't just about this one cosmic ray. It's about whether the universe hides its deepest secrets in ways we can actually test. For now, the holographic principle remains a brilliant idea waiting for solid proof. But if cosmic rays ever do crack the code, it would rewrite not just astrophysics, but our very understanding of reality itself. And as we'll see next, the cosmos has even stranger puzzles in store. Now, let's shift gears to something that sounds like it's straight out of science fiction, a cosmic ray that appeared to break the universe's speed limit. In 2006, detectors picked up an ultra-high-energy cosmic ray that seemed to be moving faster than light as it zipped through Earth's atmosphere. Before you start picturing warp drives or time travel, here's the twist: it wasn't actually breaking any rules. This cosmic ray, nicknamed the Speedster, was playing a clever trick on us, and the key to understanding it lies in a phenomenon called Cherenkov radiation. When particles move through a medium like air or water faster than light can travel in that same medium, they produce a faint blue glow Cherenkov radiation. It's similar to the sonic boom you get when a jet breaks the sound barrier, but with light instead of sound. The Speedster cosmic ray wasn't outpacing light in a vacuum. Nothing can do that, but it was moving faster than light could through our atmosphere, creating that eerie blue flash. This illusion happens because light slows down slightly when passing through air, while the cosmic ray, packed with insane energy, barely notices the resistance. So why does this matter? For one, it's a brilliant reminder of how relativity holds up even in extreme scenarios. The Speedster didn't defy Einstein, it just highlighted how light behaves differently under various conditions. But it also shows how cosmic rays can mess with our expectations, appearing to break laws they're actually obeying perfectly. And as we'll see next, the universe has even more ways to keep us guessing. Now, let's clear up one of the biggest misunderstandings about the Speedster cosmic ray. just because it seemed to break the light speed barrier doesn't mean it actually did. Here's the catch: when we say something is moving faster than light, we're usually talking about light speeding through empty space where nothing slows it down. But light doesn't always travel at its maximum speed. When it passes through air, water, or glass, it slows down slightly. That's why a straw looks bent in a glass of water. Light's speed changes as it moves between different materials. The speedster cosmic ray, however, didn't get the memo to slow down. Charged with ridiculous energy, it blasted through our atmosphere faster than light could in that same air, creating that telltale blue Cherenkov glow. But here's the key: it was still moving slower than light in a vacuum. Think of it like a race where one runner has to slog through mud while the other gets a clear track. The speedster wasn't breaking cosmic speed limits, it was just outpacing light in a specific, sluggish environment. This illusion is a perfect example of something called superluminal phase velocity. It's a fancy term for how waves, whether light, sound, or even ocean waves, can appear to move faster than they really do under certain conditions. Imagine a spotlight sweeping across clouds at night. The beam's edge might seem to move faster than light, but no single photon is actually breaking the rules. Similarly, the speedster's apparent speed was a trick of perspective, not a violation of physics. So why does this matter beyond just cosmic ray trivia? Because it reminds us that the universe loves to play tricks on our perceptions. What looks like a law-breaking anomaly is often just nature following its own rules in ways we're still learning to decode. And as we'll see next, cosmic rays have even more surprises up their sleeves, ones that challenge not just speed limits, but the very fabric of how we understand reality. Now let's shift our focus to one of the most puzzling cosmic rays ever detected: the Orphan. In 2010, scientists spotted an ultra-high-energy cosmic ray that left them scratching their heads. Why? Because when they combed through data from particle colliders, they couldn't find any known particle that could have produced it. It was like finding a fingerprint at a crime scene, but no suspect in the database. This cosmic ray didn't just break the mold, it shattered it. Normally, high-energy particles detected in space have counterparts we've seen in experiments here on Earth. But the Orphan had no match. That led researchers down a rabbit hole of wild possibilities. Could this particle be something beyond our current physics? Something like a super-Planckian particle? These hypothetical entities are thought to exist at energy scales so high they defy our understanding of quantum mechanics and gravity. Then there's the even more mind-bending idea: extra dimensions. Some theories suggest that particles from hidden dimensions could occasionally leak into our own, appearing as unexplained cosmic rays. Imagine our universe as a sheet of paper, and these particles as ink bleeding through from another sheet stacked beneath it. The Orphan might have been one of those rare glimpses into a deeper layer of reality. Of course, not everyone's convinced. Skeptics argue it could just be a fluke, a statistical outlier, or a misread signal. But here's the thing: the Orphan isn't alone. Other unexplained cosmic rays have shown similar gaps in their origins, hinting that there might be a whole family of these mystery particles out there. So what does this mean for physics? It's a wake-up call. The Orphan forces us to ask whether our current models are complete, or if there's a whole new frontier of particles and forces waiting to be discovered. And as we'll see next, cosmic rays aren't just challenging our theories, they might be rewriting the rules entirely. Now, let's take a closer look at some of the wildest ideas physicists have proposed to explain the Orphan. If this cosmic ray doesn't fit into our current understanding of particles, what else could it be? One leading candidate is something called a slepton. In theories that extend beyond the standard model, sleptons are hypothetical partners to the electrons and neutrinos we know. Think of them as shadow versions of familiar particles, but with properties just different enough to explain why we've never spotted them in colliders. Then there's the axino, a sneaky particle linked to dark matter. Some theories suggest accinos could carry enormous energy while barely interacting with ordinary matter, making them nearly invisible to our detectors. If the Orphan was an accino, it would be like catching a ghost mid-flight, leaving no trace except for that jaw-dropping burst of energy. But here's the twist: despite years of searching, experiments like the Large Hadron Collider have found no evidence for these exotic particles. That doesn't necessarily mean they don't exist. It might just mean they're too heavy or too rare for our current machines to produce. It's like trying to catch a whale with a fishing net designed for minnows. This leaves scientists at a crossroads. Either the Orphan was a freak accident, a 1 in a billion fluke, or it's a sign that we need to rethink how we search for new physics. Maybe the answers lie not in bigger colliders, but in sharper cosmic ray detectors or even entirely new experiments. One thing's for sure: the Orphan isn't just a mystery, it's a challenge. And as we'll see next, cosmic rays have a way of turning our assumptions upside down. Now, let's shift our gaze to a cosmic ray event that unfolded under one of nature's most dramatic backdrops, a solar eclipse. In 2019, detectors picked up an ultra-high-energy cosmic ray just as the moon's shadow swept across Earth. The timing was so uncanny that scientists couldn't help but wonder, did the eclipse play a role in what they were seeing? At first glance, it might seem like pure coincidence. After all, cosmic rays bombard Earth constantly, and eclipses happen regularly. But here's where it gets intriguing. The moon's shadow isn't just a dark patch, it's a temporary shield against the sun's low-energy particles, which normally create a noisy background for detectors. With that interference suddenly muted, researchers had a rare chance to study high-energy events in near-perfect conditions. So, did the eclipse actually alter the cosmic ray's behavior? The answer isn't straightforward. While the moon's shadow doesn't directly affect ultra-high-energy particles, they're too powerful to be blocked or bent by something as small as the moon. It did clean up the data. Think of it like turning off a buzzing fluorescent light to hear a faint whisper more clearly. The eclipse didn't change the whisper, but it made it easier to detect. This event also offered a unique calibration opportunity. By comparing cosmic ray rates during the eclipse to normal conditions, scientists could fine-tune their detectors, filtering out background noise more effectively in future observations. It's a reminder that sometimes the universe hands us the perfect experiment if we're paying attention. And as we'll see next, cosmic rays have even more surprises in store when they collide with our planet's atmosphere under unusual circumstances. Now, let's take a closer look at what makes this eclipse event so special when it comes to cosmic ray detection. Under normal conditions, our atmosphere is flooded with low-energy particles from the sun, creating a constant buzz that detectors have to sift through. But during a solar eclipse, something fascinating happens. The moon's shadow acts like a temporary filter, blocking out much of that solar noise. This gives scientists a rare, almost pristine environment to study ultra-high-energy cosmic rays without the usual interference. The difference is striking. When researchers compared data from the 2019 eclipse to typical observations, they noticed a significant drop in low-energy background signals. It's like trying to listen to a quiet conversation in a crowded room. Suddenly, with the crowd gone, every word becomes crystal clear. This clean data allowed detectors to pick up the ultra-high-energy cosmic ray with unmatched precision, offering clues about its energy and trajectory that might have been muddled otherwise. But the real value of these eclipse observations goes beyond just one event. By studying how cosmic ray rates change during an eclipse, scientists can fine-tune their detectors to better separate high-energy signals from background noise even under normal conditions. Think of it as calibrating a high-tech microphone. Once you know exactly what interference sounds like, you can filter it out more effectively. This kind of calibration is crucial for spotting the faintest, most elusive cosmic rays, the ones that might hold answers to the universe's biggest mysteries. And here's the kicker: these findings don't just apply to eclipses. The lessons learned from these rare events help improve detector accuracy year-round, making every observation sharper. So while the Moon's shadow might only last a few minutes, its impact on cosmic ray science lingers far longer, proving once again that sometimes the universe gives us the perfect laboratory if we know how to use it. Now let's turn our attention to something truly mind-bending: the 1995 detection of what scientists call the primordial cosmic ray. This wasn't just another high-energy particle. What made it stand out was its composition. It carried a helium-4 nucleus, the same kind of helium that formed in the first few minutes after the Big Bang. That's right, this cosmic ray might have been a relic from the birth of the universe itself. But here's the puzzle: particles that old shouldn't still pack such an energetic punch. Think about it, the Big Bang happened roughly 13.8 billion years ago. Over that unimaginable stretch of time, any particle traveling through space should have lost most of its energy, slowed down by collisions with cosmic microwave background radiation or deflected by magnetic fields. Yet this helium nucleus arrived with energy levels that rival some of the most powerful cosmic rays we've ever detected. So how did it retain so much energy? One theory suggests it might have been reaccelerated somewhere along its journey, perhaps by a supermassive black hole or a shockwave from a galaxy cluster collision. But even that doesn't fully explain why it still resembles primordial material rather than being altered by eons of cosmic travel. Another idea is that it didn't come from as far away as we think. Maybe it's been bouncing around our local galactic neighborhood, preserving its ancient signature in ways we don't yet understand. Whatever the answer, this cosmic ray challenges our assumptions about how particles age and lose energy over time. It's like finding a perfectly preserved fossil that somehow still has the energy of a living creature. And that's what makes it so fascinating. It's not just a messenger from deep space, but possibly a time capsule from the very dawn of existence. Now, shifting our focus to the cosmic stage itself, let's unravel how these high-energy relics differ from the cosmic microwave background radiation, or CMB, that fills the universe. While the CMB is like a faint, uniform glow left over from the Big Bang, a snapshot of the universe when it was just 380,000 years old, cosmic rays are more like energetic bullets, individual particles racing through space with staggering speeds. The CMB photons have lost almost all their original energy over billions of years, stretched and cooled by the expansion of the universe. But cosmic rays, especially ones like the primordial helium nucleus we just discussed, seem to defy that cooling. They arrive with energies that suggest they've somehow resisted the universe's relentless slowdown. This raises a tantalizing question: could conditions in the very early universe, before the rapid expansion known as inflation, have preserved these ultra-high energies? Some theorists speculate that in those first chaotic moments, space might have been threaded with unimaginably strong magnetic fields or crisscrossed by violent shockwaves. These extreme environments could have acted like cosmic accelerators, boosting particles to energies so high that even 13.8 billion years of travel couldn't fully drain them. Others wonder if these rays might have originated in regions of spacetime where the laws of physics operated differently, places where energy wasn't as easily lost to the surrounding void. Then there's the wilder idea that these particles aren't just relics but active participants in a hidden layer of cosmic history. Could they be evidence of phenomena we haven't even imagined yet, like defects in the fabric of spacetime or the decay of exotic matter from the universe's first seconds? Every detection of a primordial cosmic ray is like finding a clue in a billion-year-old mystery, hinting at forces and events that shaped reality before stars or galaxies even existed. What's clear is that these particles aren't just oddities, they're windows into the most extreme conditions the universe has ever known. And as we piece together their stories, we might just rewrite our understanding of how everything began. Now let's turn our attention to a cosmic ray that seemed to dance its way through detectors, the so-called jitterbug event of 2004. This ultra-high-energy cosmic ray didn't just streak through the atmosphere like most others. Instead, its signal flickered and wobbled in a way that left scientists scratching their heads. Normally, cosmic rays produce clean, predictable patterns when they collide with Earth's atmosphere, creating cascades of particles that detectors can easily trace. But the jitterbug's signal was anything but normal. It oscillated erratically, almost as if it were being jostled by something invisible along its path. This bizarre behavior led researchers to consider some mind-bending possibilities. One of the most intriguing is the idea of space-time foam, a theoretical concept suggesting that at the tiniest scales, the fabric of spacetime isn't smooth but frothy like a turbulent sea. According to this idea, the universe at the quantum level might be filled with fleeting bubbles of energy, constantly forming and dissolving. For a high-energy particle like the jitterbug, traveling through this foam could be like trying to walk straight on a trampoline while someone else is jumping on it. The particle's path might get subtly twisted, causing the strange oscillations observed in the detectors. Of course, space-time foam remains speculative. It's a prediction of certain quantum gravity theories, but we don't yet have direct evidence it exists. That's what makes the jitterbug so fascinating. If its wobbles really were caused by space-time foam, it could mean cosmic rays are inadvertently giving us a glimpse into the quantum structure of the universe itself. Some physicists even suggest that studying ultra-high-energy cosmic rays might one day help us test theories of quantum gravity, bridging the gap between the tiny world of particles and the vast scale of cosmology. But not everyone's convinced. Skeptics point out that the jitterbug's odd signal could have more mundane explanations, like instrumental glitches or interactions with magnetic fields we don't fully understand. Yet the possibility that we're seeing hints of quantum spacetime in action is too tantalizing to ignore. Whether it's spacetime foam or something else entirely, the jitterbug reminds us that the universe still holds mysteries waiting to be unraveled, one cosmic wiggle at a time. Now let's peel back the layers of this quantum mystery a little further. Spacetime foam might sound like something out of science fiction, but it's a serious idea in physics, one that could reshape how we understand the universe. Picture spacetime not as a smooth, unbroken sheet, but as a bubbling, churning ocean at the smallest scales imaginable. These tiny fluctuations, far smaller than an atom, might be constantly warping and twisting the fabric of reality itself. For something as energetic as the jitterbug cosmic ray, barreling through this quantum froth could be like a speedboat hitting choppy waves, causing those strange wobbles in its signal. This isn't just about cosmic rays acting oddly, it's about whether they could be our window into the realm of quantum gravity. At the Planck scale, where the rules of Einstein's relativity and quantum mechanics collide, our current physics breaks down. If ultra-high-energy cosmic rays are sensitive to these extreme conditions, they might offer clues about how to stitch these two theories together. Imagine using particles from deep space as tiny probes, revealing secrets about the universe's most fundamental structure. Some researchers even speculate that cosmic rays could carry imprints of extra dimensions or exotic particles predicted by string theory. But here's the catch: proving any of this is incredibly tough. The Planck scale is so mind-bogglingly small that direct experiments are impossible with today's technology. That's why cosmic rays are so intriguing. They're nature's own particle accelerators, reaching energies we could never replicate in a lab. The jitterbug's behavior might hint at quantum gravity effects, but skeptics argue we're still a long way from definitive proof. Could the wobbles be caused by unknown magnetic fields? Or maybe our detectors just need better calibration. These questions keep the debate alive. What's exciting is that every unexplained cosmic ray pushes us closer to answers. Whether it's spacetime foam or another radical idea, these high-energy messengers challenge us to think bigger. They remind us that the universe is far weirder and more wonderful than we've yet discovered. And who knows, the next cosmic ray that streaks through our detectors might just carry the clue that cracks quantum gravity wide open. Now, let's turn our attention to something truly uncanny, the mirror event of 2017. Picture this: a high-energy cosmic ray slams into Earth's atmosphere, and when scientists trace its path back into the cosmos, they realize it came from a spot in the sky exactly opposite to where another famous cosmic ray had originated years earlier. It's as if the universe lined up these two particles like perfect reflections, one arriving from the north, the other from the south. The odds of this happening by pure chance astronomically low. Think of it like throwing two darts at a globe blindfolded and hitting precise antipodal points twice. Researchers crunched the numbers and found the probability to be less than 1 in a million. That kind of coincidence doesn't just raise eyebrows, it demands an explanation. Could there be something special about these mirror points in the cosmos? Some hidden structure or symmetry we've yet to uncover? One theory suggests these rays might be coming from opposite ends of a colossal cosmic accelerator. Perhaps a supermassive black hole or a galaxy cluster acting like a particle cannon, firing bursts in two directions at once. Another idea points to the large-scale structure of the universe itself. The cosmos isn't just a random scatter of galaxies. It's woven into vast filaments and walls with enormous voids in between. Maybe these mirror rays are tracing some hidden pattern in this cosmic web, a fingerprint of the universe's architecture we're only beginning to see. Then there's the wild card. What if these rays aren't from two separate sources at all? Some physicists have floated the idea that a single, unimaginably powerful event, like a collision of cosmic strings or a decay of exotic dark matter, could have sent particles racing in opposite directions like shrapnel from an explosion. If true, it would mean these two cosmic rays, separated by years, are actually siblings, born from the same cataclysmic moment. Of course, skeptics aren't convinced. Could it just be a fluke, a trick of statistics in a universe where strange things happen all the time? After all, with enough cosmic rays detected over decades, even the unlikeliest alignments might eventually occur. But the mirror event sticks in scientists' minds because it's not just about chance, it's about whether the universe is trying to tell us something. Every time we spot a cosmic ray that defies expectations, it's a nudge to look deeper, to question what we think we know. And if there's one thing these high-energy mysteries have taught us, it's that the universe loves a good puzzle. Now, let's take a closer look at the big picture, the cosmic map that might hold the key to these mirror events. Scientists have spent decades cataloging the arrival directions of ultra-high-energy cosmic rays, and when they plot them across the sky, something fascinating emerges. It's not just random noise. There are hints of patterns, subtle symmetries that could explain why some rays arrive as perfect opposites. Imagine the universe as a vast, interconnected web. Galaxies cluster along sprawling filaments with enormous voids stretching between them. These structures aren't just passive backdrops, they shape how cosmic rays travel. Magnetic fields twist their paths, and the distribution of matter might funnel them in unexpected ways. When researchers overlay the arrival directions of mirror events onto this cosmic web, they sometimes line up with these large-scale features. Could these rays be tracing the hidden scaffolding of the universe? One compelling idea is that certain regions of space, like superclusters or dense galaxy walls, act as cosmic mirrors, reflecting or redirecting particles in ways we don't yet fully understand. For example, if a high-energy ray gets deflected by a massive galaxy cluster, it might appear to come from a completely different part of the sky than its true origin. And if another ray gets bent in the opposite direction by a similar structure, voila, you've got a mirror event. But here's the twist: the universe isn't perfectly symmetrical. While some areas show these intriguing antipodal pairs, others don't. That's led scientists to wonder whether the mirror events we've seen are just the tip of the iceberg. Maybe there's a subset of cosmic rays, those with the highest energies or specific compositions that are more likely to follow these mirrored paths. Or perhaps the symmetries we're spotting are fleeting, tied to temporary alignments of cosmic structures that shift over millions of years. To dig deeper, astronomers are now using next-generation observatories to map the sky with unprecedented precision. By combining data from cosmic ray detectors with galaxy surveys and magnetic field measurements, they're piecing together a 3D atlas of how these particles journey through space. Every new mirror event adds another clue, another dot to connect in the grand puzzle of the cosmos. And if there's one thing we've learned, it's that the universe has a way of surprising us. Just when we think we've got it figured out, it throws another cosmic curveball our way. Now, let's shift our focus to one of the most baffling cosmic ray events ever recorded, the case of the vanishing particle. Back in 2002, detectors picked up something truly bizarre, an ultra-high-energy cosmic ray that seemed to vanish into thin air. Imagine tracking a high-speed particle as it barrels through Earth's atmosphere, creating a visible shower of secondary particles, only for that shower to suddenly stop mid-detection. It's like watching a meteor streak across the sky and then blink out of existence before hitting the ground. Scientists were left scratching their heads. How could something with that much energy just disappear? One leading theory suggests this cosmic ray might have decayed into something invisible: sterile neutrinos. Unlike regular neutrinos, which barely interact with matter, sterile neutrinos are even more elusive. They're hypothetical particles that don't respond to any force except gravity, making them nearly impossible to detect directly. If this ultra-high-energy particle transformed into sterile neutrinos mid-flight, it would explain why the atmospheric shower vanished without a trace. It's as if the particle stepped into a hidden dimension, leaving no further clues behind. But here's where things get even more intriguing. Sterile neutrinos aren't just a wild guess, they're also a prime candidate for dark matter. If this vanishing act was indeed caused by sterile neutrinos, it could mean we've accidentally stumbled onto a piece of the dark matter puzzle. Picture this: a single cosmic ray event potentially bridging two of astrophysics' biggest mysteries, ultra-high-energy particles and the invisible stuff that makes up most of the universe's mass. Of course, not everyone's convinced. Some researchers argue the disappearance could be a fluke, a detector glitch, or an unusual atmospheric interaction. Others point out that if sterile neutrinos were responsible, we'd expect to see similar vanishing acts more often. Yet, this remains the only recorded event of its kind, making it both tantalizing and frustrating for scientists. To solve the mystery, newer observatories are now on the hunt for similar events, armed with better technology and sharper eyes. If they catch another vanishing cosmic ray, it could finally give us the evidence needed to confirm or rule out the sterile neutrino theory. Until then, this 2002 anomaly stands as a ghostly reminder of how much we still don't understand about the high-energy universe. And if history's taught us anything, it's that the cosmos loves to keep us guessing. Now, let's take a closer look at why sterile neutrinos have become such a compelling piece of this cosmic puzzle. When we compare them to ordinary neutrinos, the ones we've actually detected, the differences are stark. Regular neutrinos are already ghostly particles, barely interacting with matter, but they do have one telltale behavior: they oscillate. That means they can switch between different types: electron, muon, and tau neutrinos as they travel through space. This phenomenon has been confirmed in experiments like Super Kamiokande and Ice Cube. But sterile neutrinos, if they exist, they'd take this elusiveness to another level. They wouldn't oscillate in the same way because they'd completely ignore the weak nuclear force, the only interaction regular neutrinos respond to. So why do some scientists champion sterile neutrinos as dark matter candidates? It all comes down to their potential to solve multiple mysteries at once. Dark matter makes up roughly 27% of the universe's mass, yet we've never directly observed it. Whatever it is, it doesn't emit, absorb, or reflect light just like sterile neutrinos wouldn't. But here's the kicker: sterile neutrinos could also explain another head-scratcher: the observed shortage of neutrinos in certain experiments. If some neutrinos are transforming into sterile versions mid-flight, that would account for the missing detections. It's a 2-for-1 deal that's hard for theorists to resist. That said, the case isn't airtight. Critics point out that if sterile neutrinos are dark matter, they'd need just the right mass, not too heavy, not too light, to match cosmological observations. Too massive, and they'd clump differently than dark matter appears to. Too light, and they'd move too fast to form the large-scale structures we see in the universe. It's a Goldilocks problem that hasn't been solved yet. The hunt for answers continues. Experiments like the upcoming Deep Underground Neutrino Experiment, or DUNE, are designed to probe these questions with unprecedented precision. If sterile neutrinos are real, and if they're behind events like our vanishing cosmic ray, we might finally get the evidence we need to crack both the dark matter enigma and the mystery of ultra-high-energy particles. Until then, this cosmic whodunit remains wide open, a reminder that sometimes the most exciting science happens in the gaps between what we know and what we've yet to discover. Now, shifting our gaze to something truly unexpected, let's talk about the cosmic ray that left a ghostly trail of light in its wake. In 2022, detectors picked up an ultra-high-energy cosmic ray with a bizarre twist hours after its arrival. Faint ultraviolet emissions flickered in the same patch of sky. This eerie afterglow wasn't part of the initial particle shower, and that's what made it so puzzling. Was it just a cosmic coincidence, like a distant supernova flaring up at the wrong moment, or was it something entirely new? At first glance, the supernova explanation seems plausible. These stellar explosions can produce lingering UV light, and space is full of them. But here's the catch: the timing and location were almost too perfect. The afterglow appeared precisely where the cosmic ray had struck, and the delay was just a few hours, not the days or weeks typical of supernova remnants. That tight alignment raised eyebrows. Could the cosmic ray itself have triggered the UV emissions somehow? Theorists scrambled for answers. One tantalizing idea involves actions, hypothetical particles that could convert into photons under the right conditions. Picture this: the cosmic ray, as it barrels through space, might have interacted with galactic magnetic fields, producing actions along its path. Those actions could then decay into UV light hours later, creating the afterglow. It's a stretch, but not impossible. Another wild card: primordial black holes. If one of these ancient, tiny black holes evaporated near the cosmic ray's path, the burst of radiation might explain both the high-energy particle and the delayed glow. Of course, skeptics aren't convinced. They argue that with billions of galaxies and countless supernova, coincidental alignments are bound to happen. Without a repeat observation, it's hard to rule out plain old bad luck. But that's the thrill of cosmic ray science sometimes. The most tantalizing clues are the ones that refuse to fit neatly into our models. Whether this afterglow was a fluke or a fingerprint of new physics, it's a reminder that the universe still has surprises up its sleeve. And as detectors grow more sensitive, we might just catch another one in the act. Now, let's peel back the layers of this cosmic mystery and explore how delayed emissions like the 2022 afterglow could actually happen. One of the most intriguing possibilities involves actions, those elusive particles that have teased physicists for decades. Imagine a cosmic ray racing through the galaxy, surrounded by tangled magnetic fields. As it moves, it could generate actions particles that slip through space almost unnoticed. But here's where it gets wild. Those actions might not stay invisible forever. If they encounter just the right conditions, they could transform into photons, bursting into UV light hours after the original cosmic ray arrived. It's like a cosmic echo, where the initial impact sets off a chain reaction we only see later. But actions aren't the only players in this game. Another twist involves the fabric of space itself. Galactic magnetic fields are far from uniform. They twist, turn, and amplify in unexpected ways. If a cosmic ray's energy gets tangled in these fields, it could create a kind of storage effect where the energy is temporarily trapped before being released as light. Think of it like winding up a toy and watching it unwind slowly. The delay between the cosmic ray and the afterglow could be the universe's way of unraveling that stored energy at its own pace. Then there's the wild card, primordial black holes. These hypothetical remnants from the early universe could be lurking unseen, and if one happened to evaporate near the cosmic ray's path, the energy released might explain both the high-energy particle and the delayed glow. It's a long shot, but in a universe full of surprises, it's worth considering. Of course, none of these ideas are easy to prove. Detecting actions or spotting a vanishing black hole requires technology we're still refining. But that's what makes cosmic rays so thrilling. They force us to stretch our imaginations and question what we think we know. Whether the answer lies in particle physics, magnetic fields, or something entirely unexpected, one thing's clear: the universe loves a good plot twist. And with every strange afterglow, we get a little closer to unraveling it. Now, as we bring this cosmic journey to a close, let's take a moment to reflect on the sheer scale of these mysteries. From the "oh my god" particle-shattering energy records to the eerie silence of the 2008 dark accelerator event, each of these 50 observations has left scientists scratching their heads. Together, they paint a picture of a universe far more unpredictable than we ever imagined, where particles defy known physics, sources vanish into cosmic voids, and afterglows linger like ghostly signatures. What makes these ultra-high energy cosmic rays so extraordinary isn't just their individual oddities, but how they collectively upend our understanding of the cosmos. They force us to reconsider everything from galactic magnetic fields to the very fabric of space-time. Are we missing hidden sources like dwarf galaxies packed with dark matter? Could exotic particles or primordial black holes hold the key? Or is there an entirely new chapter of physics waiting to be written? This is where you come in. Cosmic ray research thrives on curiosity and collaboration. By supporting observatories like the Pierre Auger Array or IceCube, you're helping unravel these enigmas one detection at a time. And if you're as fascinated by these cosmic puzzles as we are, don't miss out on future deep dives. Hit that subscribe button and ring the notification bell so you never miss a mystery. The universe has thrown us 50 cosmic curveballs. Who knows what it'll reveal next? Stick around, because the greatest discoveries are still ahead. Thanks for joining us on this journey through the unknown, and remember, the next big cosmic revelation might be just one